Now is the Q&A section on projectile motion. Welcome to my advanced physics class. Kindly share, subscribe, click on the notification bell, and comment. The vector equations for projectile motion have already been established, and it is time for one application of it. A rocket is shot from the top of a cliff 300 meters above sea level at an angle of 45 degrees to the horizontal and an initial velocity u. What time does a rocket hit a boat on the sea after it has been fired? Calculate the velocity u given that the rocket hit the boat 4.2 kilometers away from the cliff. In every physics problem, especially in mechanics problem, a diagram half solves the problem. You first have to draft a suitable diagram for it with the known parameters in the problem. So over here, we know there is a cliff. That represents the cliff with this kind of vertical rectangle. The height of the cliff is 300 meters. A projectile is shot from the top of the cliff and it hits a boat at sea level. Sort of a boat here. The distance between the cliff and the boat on the sea level is 4.2 kilometers. The rocket is launched at an angle of 45 degrees to the horizontal, or pi on 4 radians. These are the given. We are also told, though not given, the actual value that it was shot. The rocket was shot at an initial velocity u, like that. So knowing these given parameters, you would know which equation to choose to solve it. So given the first vertical distance, let's write down the position function in the vertical direction. You know, a projectile has two components, a vertical then a horizontal. For the vertical position function, we have y of t is equal to an initial position y naught plus the initial velocity, which is this component of the velocity. If we resolve the velocity, we have two components. We have u sine 45 and then we have u cosine 45. So then we have u sine 45 to be the initial vertical velocity times t. Then we ask ourselves, now what of the gravity component? The acceleration due to gravity is sign sensitive. Do we pick the positive or pick the negative? It depends. It depends on how we choose our increasing direction of y. Now let's fix our Cartesian plane on top of the cliff and put our 0 at the origin here. Meaning the cliff itself is negative 300 meters downwards from the 0. So then if we choose our increasing direction of y upwards and knowing very well gravity points downwards, then g will be a negative. So we have minus half g t squared. This is the first equation we can establish. The first question is, what time does a rocket hit a boat on the sea after it has been fired? This time is referring to the time of flight that previously we denoted by capital T. So calculating the time of flight, this equation then changes to y at the time of flight, capital T, is equal to what is the initial position of the y? We picked that 0 to be the initial position, so that is 0. And this is the increasing direction of the y, and this is a decreasing direction of y. So we have u sine 45 degrees times, this time around, the time of flight, which we are looking for, minus half g. Let's take g to be 10 for simplicity. We have 5 capital T squared The 5 is got from half of 10. So it is this time of flight we are looking for. But then given one equation, there are 3 unknowns. And one equation will not suffice in getting the time of flight. We don't know y of t, we don't know u, we don't know capital T. Or maybe we know y of capital T. Yes, we do. We do because when the rocket hits the boat on the sea level, what is the final vertical distance? In other words, what is the vertical distance at the time of flight? It is red from the 0 downwards. When the rocket hits the boat on the sea level, then the vertical distance will be negative 300. We make it negative 300 because of where we picked our Cartesian plane. If the 0 is fixed here and our increasing y direction is like so, then downwards will be negative. So negative 300 is equal to, we have u, which is an unknown, sine of 45 times the time of flight minus 5 t squared. We have reduced the equation into 2 unknowns, capital T and then u. There is nothing else we can do with this equation. And if there are 2 unknowns, we need a second equation to be able to solve for the time of flight. So let's look out for other givens within the question. We are given also the range that the rocket travels. That is 4.2 kilometers. And the kinematic equation for that is x of capital T, which represents the range, is going to be equal to the initial velocity cos the angle given, which is pi on 4 radians, which is 45 degrees, of course, times the time of flight. So then we know the range, x of capital T, which is 4,200 meters. 4.2 kilometers converted to SI unit, we have 4,200 meters, is equal to u cos 45 then times capital T. We are looking out for capital T. So to be able to do that, we have 2 equations, 1 and then 2. Let's make u the subject and slot it into the first equation. We have u to be equal to 4,200 divided by cos 45 times the time of flight. And having done that, let's put this equation into this. We have negative 300 is equal to u. We know u now. U is 4,200 over cos 45t. So 4200 divided by cosine of 45 capital T. That is u. Times sine 45 capital T minus 5 t squared. So we put this here. The advantage of that is capital T cancels capital T. And then we have sine 45 divided by cos 45. We have tangent of 45 degrees. So negative 300 is equal to 4,200, the tangent of 45, and then minus 5 capital T squared. Now we are almost done because we are getting only one arbitrary capital T here. Let's make that the subject. So we then write 5t squared is equal to 4,200 tangent of 45 plus 300. We're able to do that when 5t squared is sent to the left and negative 300 is sent to the right. So making t the subject, we have t is equal to the squared root of 4,200 tangent of 45 plus 300 divided by 5. And that is the time of flight. Any calculator, say scientific, would give us a straightforward answer. All that we need to do is to punch every value over there. Square root of 4,200 times 45 plus 300 divided by 5 is the time of flight. The follow-up question is calculate the velocity u, given that the rocket hits the boat 4.2 kilometers away from the cliff. So we can use this equation to directly solve for u, knowing the time of flight. If you get the value for time of flight, say on a calculator, and you put it here, you have u. Thanks for watching our first problem under projectile motion. Once again, click on the notification bell, subscribe, comment, and share. Our next is going to be circular motion, which is another application of position function in a vector form. Stay tuned. We cannot close the episode without showing this. We are showing that for every projectile motion, the position y is parabolic with x. In other words, y is equal to x tan theta minus g sec squared theta over 2u squared times s squared. So given every x position and given the initial velocity as well as the initial angle of projection, you can simply calculate for y. So this is the trajectory function of y in terms of x. Let's show that. And this equation can be shown knowing very well that for every projectile motion, the time evolution of the vertical position function is equal to the initial position, which is y naught, and then plus u sine theta, of course, times t, and then minus half gt squared. That is if you choose your increasing direction of y upwards. And then x as a function of t, every horizontal distance is equal to the initial horizontal distance plus u cos theta times time. If we juggle these equations, we are going to show this. So what we do is we are going to make the time dependence vanish. Let's make t the subject here and slot it into this equation. So from the second equation, t is equal to x at any point in time minus the initial x position x naught, now divided by u cos theta. That is t. Then we put the value of t into the first equation. We have y of t. So then y will no more be a function of t. If you put the value of t at every part of the equation, then t will vanish. So we have y, simply y, which will now be a function of x, is equal to, it will be a function of x at a constant theta and at a constant initial velocity, is equal to y naught plus u sine theta times time. And now we know the time to be x of t minus x naught divided by u cos theta. Then we have minus half g into bracket t, that is x of t minus x naught divided by u cos theta all squared. Well, it is a t squared dependent. So what do? We have some commonalities over here. We have u cancelling u. Of course, sine theta over cos theta is tangent of theta. So the equation reduces to y of x is equal to, we have the initial vertical position plus sine theta over cos theta, we have tangent of theta, times x of t minus x naught. So we have x of t minus x naught, the tangent of theta. Then we have minus this component here. Now squaring everything, we have x of t squared, that is this quantity squared. In other words, this x of t function is squared. So the whole of this is squared minus 2 times x of t times x naught plus x naught squared. So the square of this top quantity, the numerator, is going to be x of t squared minus 2 times x of t x naught, then plus x naught squared. Before we divide by u squared cos squared theta. Then we multiply everything by half of g. So times half of g. That's what we have. With the whole of this divided by u squared cos squared theta. The whole of this quantity divided by this and times half of the g. So then y of x is going to be equal to y naught plus, now s of t minus x naught, let me simply call that delta x. So delta x times tan theta minus, we have x of t squared minus 2, let me put that here, so minus x of t squared minus 2 times x of t times x naught plus x naught squared, all divided by u squared cos squared theta, then times half of g. So that half of g, we are going to put it here, half g. Now our y naught and x naught can be chosen to be at anywhere. If we choose y naught to be 0 and x naught to be 0, then y of x is equal to, this becomes 0, and then this delta x, when we choose our initial horizontal position to be 0, x naught to be 0, delta x will simply be x. In other words, this quantity here, if this is 0, it reduces to x. So we have x tan theta minus, if x naught is 0, this is 0, and this is also 0. So then we have x squared, which is this quantity squared, divided by u squared cos squared theta times half g. And the final equation, y of x is equal to x tangent of theta minus, now the reciprocal of cos squared theta is secant squared theta. So this quantity 1 over cos squared theta is secant squared theta. So we have g, which is a numerator, times secant squared theta times the s squared here. This is a times. Let me change that to a dot to separate that from this one. So times s squared, then divided by this 2u squared. So for every projectile motion, if the initial position is chosen to be 0, 0 at a chosen origin, then y of x is equal to x tangent of theta minus g secant squared theta s squared over 2u squared, as demanded over here. This is a very good equation in solving most of the projectile problems. And even with a just solved problem, when we were looking for u, could have used this equation, putting negative 300 here, putting 4,200, putting 45 here, 45 there. We know g to be 10. Then we know x to be 4,200. Just make u the subject and you're cool to go. This is the end of the episode. Our next video is on circular motion. Stay tuned as we discuss some interesting physical concepts about circular motion.